To close out this chart, I like to go back to table 3.2 and find the fully plastic moment for each trial shape. Now phi MP, or the fully plastic moment, is the strongest inflexure that any particular shape could get, no matter how high C sub B is. So going back to table 3.2, our first trial was a 21 by 44, and we see that phi MP is 358. Likewise, for the other shapes, we have 398. For the trials in segment B, 600 and 664. And for segment C, we have a duplicate trial, so that's 398. And for the 18 by 55, we find that its phi MP is 420. Now, probably a while ago, you may have caught on to the fact that we probably did more work than we had to get this chart. Just by looking at MU, CB, and L sub B, we can oftentimes find out which segment will govern. So we're looking for the ones with the longest unbraced length, the shortest C sub B, the smallest C sub B's, and the highest M sub U's. Now it turns out we have all three of those things, worst case scenarios, in segment B. Segment B has the highest moment of all three segments, the lowest C sub B, and the longest L sub B. So we probably could have just focused in on segment B all along. But we went through segment A, B, and C just for practice. Now, once we have phi M sub P for all of our trial shapes, we want to see if we can rule out any of these trials. We do that by comparing phi M sub P to M sub U. And in segment A, 358 and 398 are both less than M sub U. So that tells us when we use table 310 to get us in the ballpark, we assumed we could use all of the C sub B, the full 1.5, when in reality we're not going to be able to. Assuming we can use that full 1.5 C sub B puts our assumed strength beyond the roof, or beyond phi M sub P, which is not possible. So both of these trials are ruled out. Now if we thought segment A would govern, we'd have to go back into table 310, go across 8 feet unbraced length and go up that 8-foot line until we have maybe 1 or 2 or maybe even 3 more solid lines that we cross, and write those down as trial shapes and see if those work. But we're not going to worry about that. We're going to move on to segment B, which we know governs. Now segment B, we have 600. That is greater than 507.7, and so is 664. So those are still viable options. For segment C, 398, well, we ruled out the 21 by 48 shape in segment A. So if it's not good for segment A, it's not going to be good for our entire beam, and we shouldn't even consider it in segment C. 420 is also lower than 472.5, and so the W18 by 55 has been ruled out. So moving forward, we want to choose our lightest trial shape that passes our initial test, and then check to see if that shape works for all three segments. So the two shapes we have left that are feasible are the W21 by 68 and the W24 by 68. So they're both the same weight, but we're going to go with the W21 by 68 because it's shorter. So now we need to check to see if that will work. So check W21 by 68. And we need to go to table 3.2 and get some important information about this W21 by 68. So while we're there, we'll copy down LP, 6.36 feet, LR, which is 18.7 feet, IX, which is 1480 inches to the fourth, phi times the bending factor, which is 18.8 kips, and phi V sub n, which is the design shear strength, 272 kips. So we have all the pertinent information we need to know about this trial shape. Now we're going to confirm it works for all three segments. So in segment A, we know that the design strength is equal to C sub B times the design strength when C sub B equals 1.0. And we get that by going into table 310. So our trial segment, our trial shape, the 21 by 68, was found looking at segment B. We need to make sure it works for segment A. So we're going to enter table 310 using the segment A parameter of an 8-foot unbraced length. So we're going to go to table 310, keep going down until we get around 8 feet here and 21 by 68, so it may be a while. Okay, so we have 8 feet, and what we're going to do is go up this 8-foot mark until we hit the 21 by 68, and we should hit that around, let's see if we can find it. Yep, here it comes. So 21 by 68 crosses 8 feet right about at 570 kip feet. So C sub B is 1.50, we should calculate it. Multiply that by that 570 kip feet we just got from table 310, and we get 855 kip feet. Now we have to have a little wherewithal and realize that phi m sub n can never exceed phi m sub p, so we're going to cross that out and say it's equal to 600, which is phi m sub p. And since phi m sub n equals 600, and that is greater than or equal to m sub u in segment A, which is 410 kip feet, we're okay, and the W21 by 68 works in segment A. Now for segment B, we're going to do the same thing. Phi m sub n is equal to C sub B times the value of phi m sub n you'd get from table 310, and we'd find out that we would get 538.6 kip feet, which is greater than or equal to mu of 507.7 kip feet, therefore we're okay. And in segment C, the unbraced length is 6 feet. That's less than L sub P, and so right away off the bat, we know that phi m sub n is equal to 600 kip feet, no matter what C sub B was. So that's greater than m sub u of 472.5, and therefore it's okay. So the last thing we need to do with this 21 by 68 to ensure it works for flexure in our beam is to account for self-weight. Now for a simply supported beam with a uniform distributed load, we know the equation for max moment is WL squared over 8. We're going to use that, however we have to be cognizant that that's going to be a little conservative. That won't give us the actual value of moment due to self-weight because, well, when we superimpose that WL squared over 8 on top of the max moment in segment B, the problem is the max moment in segment B isn't exactly in the middle of the beam. So we're superimposing two values of max moment, one from loads, one from self-weight. Problem is they're not actually occurring along the same point in the beam. That's okay for our purposes. We're going to be conservative and say that the max moment overall, m sub u, is equal to 507.7 kip feet plus WL squared over 8 due to self-weight, which equals 507.7 kip feet plus, got to remember to factor the self-weight, 1.2 times 0.068 kips per foot times 24 feet quantity squared over 8. So we'll assume 1.2 dead plus 1.6 live controls. And we'll say mu is then going to be equal to 513.6 kip feet, which is still less than or equal to phi mn, which is 538.6 kip feet. Therefore, the W21 by 68 is good in flexure for this case. We need to move on to shear. So check shear is next. Now shear is the largest shear in the beam is the right support reaction. So VU is going to be 138.75 kips. That's less than or equal to phi VN, which is 272 kips. Therefore, this beam is okay in shear. That was easy. One last thing to do, and that's check deflection. You have to make some assumptions to check deflection. Deflection is easiest to check in visual analysis when you can model the loads exactly as they are and let the computer do the work for you. However, we're going to do two things. One, assume that all the loads that are applied are due to live loads. And so when we want to find the service live loads, we just need to divide the W sub U's that were given in the problem, that were 5 kips per foot and 20 kips per foot, by 1.6 to unfactor them. Then we have the problem that we have two different values of distributed loads, and it's going to be complicated to solve for deflection by hand. So one way to make an assumption that makes it easier for us to solve deflection by hand is to take a look at the total load being applied on this building. We have 20 kips per foot across the far right 6 feet, and we have 5 kips per foot applied on the leftmost 18 feet. That's a total of 210 kips. If we were to kind of peanut butter spread that 210 kips across the whole beam, we would have a WU of 8.75 kips per foot. So we'll assume that for starters. And when we back off by 1.6 for the live load factor, then we have WL equal to 5.47 kips per foot. So these are two assumptions that we're going to make. They're both conservative. Spreading out a load evenly when loads had previously been higher towards the side will make our deflection greater than our real beam would experience. And then again, assuming the whole thing is live load, because live load is the only thing that comes into play when we account for deflection, is also a conservative assumption. So oftentimes a problem will give you more information. Here we'll just make these two assumptions. And so that we know deflection is W 5 WL to the 4th over 384 EI. And so when we plug in these numbers, we have 5 times 5.47 kips per foot times 1 foot over 12 inches times the length, 24 feet, times 12 inches per foot to the 4th over 384 times 29,000 KSI times I, which was 1480 inches to the 4th. We get a deflection of 0.95 inches. And the max deflection allowable due to a roof condition is L over 240, which is 24 feet times 12 inches per foot divided by 240, which is equal to 1.2 inches. So deflection is equal to 0.95, which is less than or equal to delta max, which is 1.2 inches. Therefore, this beam is okay in deflection. If it failed in deflection, we could back calculate and solve for the minimum I that would work to achieve a deflection under 1.2, and go into our IX tables around page 3-29 and find the lightest shape with a strong enough moment of inertia on the x-axis that works. So it works for flexure, shear, and deflection. Therefore, our final answer, use W21/68 A992 steel beam.